Welcome. Today we're diving into the fascinating world of digital circuits, focusing on adders and subtractors. These are fundamental building blocks in digital electronics, enabling computers and calculators to perform arithmetic operations. Whether you're a student, hobbyist, or just curious about how devices process numbers, understanding adders and subtractors is essential. We'll start with the basics, gradually building up to more complex concepts. By the end, you'll have a clear grasp of half and full adders and subtractors and how they fit into the bigger picture of digital computation. Let's get started on this journey into logic circuits. Before we explore adders and subtractors, let's quickly review binary arithmetic. In digital systems, numbers are represented using only two digits, 0 and 1. Adding or subtracting these binary digits called bits follows simple rules. For example, 0 plus 0 is 0, 1 plus 0 is 1, and 1 plus 1 is 10 in binary, which means 0 with a carry of 1. Subtraction also has its own set of rules. Understanding these basics is crucial, as all digital arithmetic relies on these fundamental operations. With this foundation, we can now move on to the building blocks that make binary arithmetic possible. Half adder is the simplest digital circuit that adds two single binary digits. It produces two outputs, the sum and the carry. The sum represents the basic addition result, while the carry indicates if the sum exceeds the value that a single bit can hold. Half adders are essential for understanding more complex adders and are often used as building blocks in larger circuits. They don't handle carrying values from previous additions, which is why they're called half adder. Next, we'll see how the half adder works in detail. Let's break down the logic behind a half adder. It takes two inputs, usually labeled A and B. The sum output is generated using an XOR exclusive OR gate, which outputs 1 only if the inputs are different. The carry output is produced by an AND gate, which outputs 1 only if both inputs are 1. This simple combination allows the half adder to add two bits and indicate if a carry is needed for the next higher bit. Understanding this logic is key to building more advanced arithmetic circuits. Truth table for a half adder shows all possible input combinations and their corresponding outputs. When both inputs are 0, the sum and carry are 0. If one input is 1 and the other is 0, the sum is 1 and carry is 0. When both inputs are 1, the sum is 0 and carry is 1. This table helps visualize how the half adder processes binary addition. It's a handy reference for designing and troubleshooting digital circuits. While half adders are useful, they have limitations. The main drawback is that they can't handle carry-in values from previous additions. This means they're only suitable for adding the least significant bits in a multi-bit addition. For more complex arithmetic, we need a circuit that can manage both the current addition and any carry from earlier stages. That's where the full adder comes in, addressing the shortcomings of the half adder. Full adder is a more advanced digital circuit that adds three binary digits, two significant bits, and a carry-in from a previous addition. It produces two outputs, sum and carryout. The full adder is essential for multi-bit binary addition, as it allows us to chain multiple adders together to handle numbers larger than 1 bit. This makes full adders a cornerstone of arithmetic logic units in computers and calculators. Full adder circuit takes three inputs, A, B, and carry and sin. The sum output is generated by combining two XOR gates, while the carryout is produced using a combination of AND and OR gates. This structure allows the full adder to process both the current bits and any carry from previous additions. By connecting several full adders in series, we can add binary numbers of any length, making this circuit incredibly versatile. Truth table for a full adder lists all possible combinations of the three inputs and their corresponding sum and carryout outputs. This table is a valuable tool for understanding how the full adder processes different input scenarios. It's especially useful when designing or analyzing multi-bit addition circuits, as it shows exactly how each bit and carry-in affect the result. Add numbers larger than 1 bit, we connect multiple full adders in a series, forming what's called a ripple carry adder. Each full adder handles a single bit and passes its carryout to the next stage. This setup allows us to add binary numbers of any length, making it a fundamental component in digital arithmetic units. Understanding how to chain full adders is key to designing efficient multi-bit adders. Ripple carry adder is constructed by connecting several full adders in sequence. The carryout from each adder becomes the carry-in for the next. While this design is straightforward, it can be slow for large numbers because each stage must wait for the previous carry to ripple through. Despite this, ripple carry adders are widely used due to their simplicity and ease of implementation. One challenge with ripple carry adders is speed. Since each adder must wait for the previous carry, the total delay increases with the number of bits. This can be a bottleneck in high-speed digital systems. Engineers have developed faster adder designs such as Carry-Lookahead adders to address this issue. Understanding these limitations helps in choosing the right adder for a given application. Carry-Lookahead adders are designed to overcome the speed limitations of ripple carry adders. They use additional logic to calculate carry signals in advance, reducing the overall delay. This makes them ideal for high-speed applications where quick arithmetic operations are essential. While more complex, carry-lookahead adders are a key innovation in digital circuit design. Now let's shift our focus to subtractors. Just as adders handle addition, subtractors are digital circuits that perform binary subtraction. They're essential for arithmetic operations in computers, calculators, and other digital devices. Like adders, subtractors come in two main types, half subtractors and full subtractors. Let's explore how these circuits work. Half subtractor is a basic digital circuit that subtracts one binary digit from another. It has two inputs, usually labeled A and B, and produces two outputs, the difference and the borrow. The difference is the result of the subtraction, while the borrow indicates if the subtraction required borrowing from a higher bit. Half subtractors are simple but form the foundation for more complex subtractor circuits. Half subtractor uses two logic gates, XOR and AND. The difference output is generated by an XOR gate while the borrow output is produced by an AND gate combined with a NOT gate. This setup allows the circuit to handle basic binary subtraction, indicating when a borrow is needed. Understanding this logic is crucial for designing more advanced subtractor circuits. Truth table for a half subtractor lists all possible input combinations and their corresponding difference and borrow outputs. This table helps visualize how the circuit handles each subtraction scenario. It's a useful reference for anyone learning about digital subtraction or designing basic arithmetic circuits. Half subtractors, while useful, have their limitations. They can't handle borrow-in values from previous subtractions, making them suitable only for the least significant bits. For multibit subtraction, we need a circuit that can process both the current subtraction and any borrow from earlier stages. This leads us to the full subtractor, which overcomes these limitations. Full subtractor is a digital circuit that subtracts one binary digit from another, considering both the current bits and a borrow-in from a previous subtraction. It has 3 inputs, A, B, and borrow-in bin, and 2 outputs, difference and borrow-out. The full subtractor is essential for multibit binary subtraction, allowing us to chain several together for larger numbers. Full subtractor circuit uses a combination of XOR and OR gates to process 3 inputs, A, B, and borrow-in. The difference output is generated using 2 XOR gates, while the borrow-out is produced by combining several logic gates. This structure allows the full subtractor to handle both the current subtraction and any borrow from previous stages, making it suitable for multibit operation. Truth table for a full subtractor lists all possible combinations of the 3 inputs and their corresponding difference and borrow-out outputs. This table is a valuable tool for understanding how the full subtractor processes different input scenarios, especially when designing or analyzing multibit subtraction circuits. To subtract numbers larger than 1 bit, we connect multiple full subtractors in a series, similar to how we build multibit adders. Each full subtractor handles a single bit and passes its borrow-out to the next stage. This setup allows us to subtract binary numbers of any length, making it a fundamental component in digital arithmetic units. Ripple borrow subtractor is constructed by connecting several full subtractors in sequence. The borrow-out from each subtractor becomes the borrow-in for the next. While this design is straightforward, it can be slow for large numbers because each stage must wait for the previous borrow to ripple through. Despite this, ripple borrow subtractors are widely used due to their simplicity. Just like ripple carry adders, ripple borrow subtractors face speed limitations. Each stage must wait for the previous borrow, increasing the total delay as the number of bits grows. For high-speed digital systems, engineers have developed faster subtractor designs to address this issue. Understanding these limitations is important when designing efficient arithmetic circuits. Parallel subtractors are designed to overcome the speed limitations of ripple borrow subtractors. They use additional logic to process multiple bits simultaneously, reducing the overall delay. This makes them ideal for high-speed applications where quick subtraction is essential. While more complex, parallel subtractors are a key innovation in digital circuit design. Adders and subtractors are both essential for digital arithmetic, but they serve different purposes. Adders combine binary numbers while subtractors find the difference between them. Both circuits use similar logic gates, but their arrangements differ to handle addition or subtraction. Understanding their similarities and differences is crucial for designing efficient digital systems. In many digital systems, it's useful to have a single circuit that can perform both addition and subtraction. Combined Adder-Subtractor circuits use additional logic, such as XOR gates and control signals, to switch between the 2 operations. This flexibility makes them valuable in arithmetic logic units and processors. Combined Adder-Subtractor circuit typically uses an XOR gate to invert one set of inputs when subtraction is needed. A control signal determines whether the circuit adds or subtracts. This design allows the same hardware to handle both operations, saving space and resources in digital devices. Adders and subtractors are at the heart of every computer's arithmetic logic unit, ALU. They enable processors to perform calculations, from simple addition and subtraction to more complex operations. Understanding these circuits helps explain how computers process data and execute instructions. Calculators rely on adders and subtractors to perform arithmetic operations quickly and accurately. These circuits are embedded in the calculator's processor, allowing it to handle everything from basic math to scientific calculations. The efficiency of these circuits directly impacts the speed and reliability of the device. Embedded systems, such as those in appliances, vehicles, and industrial machines, use adders and subtractors for control and monitoring tasks. These circuits process sensor data, manage timing, and perform calculations needed for system operation. Their reliability and efficiency are crucial for the performance of embedded devices. Digital signal processing (DSP), adders and subtractors are used to manipulate audio, video, and other signals. They perform operations like filtering, mixing, and transforming data. The speed and accuracy of these circuits are vital for real-time processing in applications like audio equipment and communication systems. Adders and subtractors play a role in error detection and correction algorithms such as checksums and parity checks. These techniques help ensure data integrity during storage and transmission. By quickly calculating sums or differences, digital systems can identify and correct errors, improving reliability. The arithmetic logic unit, or ALU, is a core component of every processor. It uses adders and subtractors to perform arithmetic and logical operations. The design and efficiency of these circuits directly affect the overall performance of the processor, making them a critical focus in computer engineering. Engineers constantly seek ways to optimize adders and subtractors for speed, power consumption, and size. Techniques like pipelining, parallelism, and advanced logic gate arrangements help achieve these goals. Optimized circuits are essential for modern devices, from smartphones to supercomputers. In battery-powered devices, low power consumption is crucial. Engineers design adders and subtractors to use minimal energy while maintaining performance. Techniques like clock gating and voltage scaling help reduce power usage, extending battery life in portable electronics. As technology advances, circuits like adders and subtractors are becoming smaller and more efficient. Miniaturization allows more functionality to fit into tiny chips, powering everything from wearable devices to advanced medical equipment. This trend drives innovation in digital circuit design. Before being used in products, adders and subtractors undergo rigorous testing and verification. Engineers use simulation tools and test benches to ensure circuits work correctly under all conditions. This process is vital for ensuring reliability and preventing costly errors in finished devices. Learning about adders and subtractors is a key part of digital electronics education. These circuits provide a foundation for understanding more complex systems and inspire future engineers. Hands-on projects and simulations help students grasp the concepts and see their real-world applications. Building and testing adders and subtractors in the lab is a great way to reinforce learning. Using breadboards, logic gates, or simulation software, students can see how these circuits work in practice. Experimentation helps bridge the gap between theory and real-world application. Modern simulation tools make it easy to design and test digital circuits like adders and subtractors. These tools allow users to build virtual circuits, run simulations, and analyze results without physical hardware. Simulation speeds up the learning and design process, making it accessible to everyone. The future of adders and subtractors lies in continued innovation. As technology evolves, these circuits will become even faster, smaller, and more efficient. Advances in materials, design techniques, and computing architectures will shape the next generation of digital arithmetic circuits. Let's recap what we've learned. Adders and subtractors are essential digital circuits for arithmetic operations. Half adders and subtractors handle single bits, while full versions manage multi-bit operations with carry or borrow. These circuits are the backbone of digital computation, powering everything from computers to embedded systems. Understanding adders and subtractors equips you with the knowledge to design and analyze digital systems. Whether you're building a simple calculator or a complex processor, these circuits are foundational. Keep exploring and experimenting to deepen your understanding and skills in digital electronics. Congratulations on completing this journey through adders and subtractors. You now have a solid understanding of how these circuits work and their importance in digital electronics. Continue exploring related topics such as multiplexers, flip-flops, and memory circuits to expand your knowledge even further.